Okay, hello everybody. We're going to start today with a series of lectures on continuum physics. And I'll start by just writing down the name of the topic. Okay, now when we talk about continuum physics, there are two things to talk about. First of all, what do we mean by continuum? And when we say continuum here, we are talking about the physics of bodies that can be treated as continuous systems. An example is this foam version of an American football. Right? The idea is that this is a body that's continuous. Of course, we know that if you look at it under a sufficient degree of magnification, a sufficiently strong microscope maybe, you'll see voids in it and all of that, right? We're not concerned with that. For our purposes, this is a continuous body, okay? And that's what we mean by continuum physics. Another example is the colored fluid, just water, in this bottle, right? I can rock it gently from side to side. You see the fluid sloshing around. However, the fluid remains continuous. We know that if we really agitate it, we get bubbles and things like that, and those are not truly continuous. We won't really get into that sort of an issue in this series of lectures. Mind you, continuum physics can treat those problems too. It's just that in this sort of basic entry-level series of lectures, we won't worry about that. You may be able to see that I have drawn a little window in the front of this bottle. It doesn't concern us right now, but as we get deeper into the lectures, that window will become important to us. Okay? So we know what we mean now by continuum physics. At least we know what we mean by continuum bodies. So let's start off by putting that down. So we are talking, when we talk about continuum physics, we mean that we are concerned with bodies that can be considered to be continuous. Okay? Simple enough definition. But there is more. You know, when we talk about continuum bodies, we're obviously going to talk about other physical quantities on them. Okay? Continuum physics also requires that when we talk about other variables, other quantities of physics that are going to be important to these bodies, we are going to talk about them, we're going to describe them by continuous mathematical functions. Okay? So, bodies that can be considered to be continuous, and in addition, we're also going to talk about physical quantities. Right? Physical quantities that are described by continuous mathematical functions. Okay? And that really, in a nutshell, is what continuum physics is about. Continuum bodies subject to physical quantities, and by physical quantities we mean the usual sorts of things, right? We're talking of mass, force, velocities, and so on, but we're going to find ways to describe those quantities through continuous mathematical functions. Let's talk a little about what kinds of physics we're going to cover here, because of course physics is very broad, right? There are mainly two types of phenomena we're going to look at here. The first is mechanics. Okay? And we won't get into a formal definition of mechanics. We'll assume that everybody knows what we mean by mechanics. We're talking about, we're going to look at how bodies move, maybe how they deform, how forces are applied upon them. All of that is mechanics, okay? Furthermore, in the context of mechanics, we're going to look at the mechanics of solids and, to a lesser extent, fluids. We will mainly concern ourselves with fluids in order to understand better what we mean by a solid. Okay, so what we mean by a solid is what a fluid is not. Okay, and we will see more and more of this as we go along. The other broad phenomenon that we're going to consider towards the latter section of this series of lectures is transport. Okay. Again, when I say transport, I will assume that we know broadly what we mean. I will just say for now that we're going to look at how quantities, maybe mass, maybe heat, are transported through the bodies of interest, right? So we'd be interested perhaps in how some field of interest, like a chemical field maybe, is going to be transported through this body. Same thing with this bottle of water, right? Colored water. We may concern ourselves with how we may introduce at one end of this bottle, we may introduce a dye of some other color, I don't know, maybe red, and watch how that dye is transported through the rest of the fluid. Okay, so that's what we mean by transport. Now, so we're going to start these lectures by really looking more specifically at continuum mechanics. And in the context of continuum mechanics, we are going to look at both rigid bodies okay. By rigid body, again, we mean something that is not quite as deformable as this, right? You can see this thing deforming now. There, you can see it deforming. Instead, assume that this thing was not deformable, rigid. Right? So we will look at the mechanics of rigid bodies, right? Something that just moves without deforming. That's what we mean by rigid body. And then, of course, the converse or the opposite of a rigid body is a deformable body, right? Or deformable bodies. Okay. Those two classes really cover the sorts of bodies that we will look at. They may be fluid or solid, right? Obviously, fluids will not be rigid bodies, only solids will be rigid. But, okay, so we understand that. All right, let's plunge further now. What we want to consider ourselves with is what a continuum body is not, okay? So we know that our solid or our fluid at sufficient magnification consists of particles, or even at even greater levels of magnification consist finally of atoms, right? Or you may choose to go down into the subatomic scale as well. Okay, so let's try to represent that. So I'm going to draw our body, right? And that is how we will often represent a body, through this sort of potato, as it's often called. We know that this body actually contains atoms, right? Let me concern myself now with one of those atoms. I label it atom I. Are labeled, or can be labeled, in this case I have labeled them as I, J, K, and so on. Okay. Now, one of the basic physical quantities we are going to concern ourselves with is the mass, right? So if we want to write out the mass of this body that I've drawn here, we write it out as, we're going to use the symbol m, very obviously. We could write out the total mass of the body as the sum of the mass of individual particles, right? So this particle I that I've labeled here has mass m sub I, okay? And we just sum over all of those particles, I, right? And we get the total mass of the body. In a similar fashion, we may concern ourselves with the force acting on the body, right? The total force. Again, let's suppose that we write the force out as F, and I'm going to write this as F sub G, meaning the force due to gravity. We know how we would write this out. We would now write it as a sum, again, over I. The force acting on atom I is mi times g, where g is the acceleration due to gravity. It's a vector, and we are going to say more about vectors in just a little bit. I will denote vectors by this underbar. So let's move on. So this is essentially how we talk about the about the mass or the forces acting on individual atoms in a body. Now, the difficulty with this type of a representation is that there is often too much detail that comes with it. If you think of us writing out the mass of each one of the atoms in this body or in this body of fluid, that's going to be a bit too much, right? Likewise for the forces. Often that gives us way too much information than we can handle in most practical, let's say in most engineering applications, okay? So we're going to do things in a slightly different manner here. We're going to take a different approach, and we're going to start out by, again, looking at our body, right? We are going to denote the body now by a script B, okay? That's the body, okay? Denote okay, so we denote the body by B. And what we want to think about now is not the body itself, because this is, if we denote this body as B, it's not a very convenient representation. It's particularly not convenient from the standpoint of mathematics. We want to think about this a little differently. And the way we want to think about it is the following. This body is occupying some region in ambient three-dimensional space, right? Rather than concern ourselves with the body, it turns out that for mathematical purposes, it is better if we concern ourselves with the region in space occupied by this body, okay? So, and likewise with this fluid body, right? We are going to concern ourselves with the region occupied in space by this body, by that fluid body. So, if we denote the body by B and the region of three-dimensional space and the region of 3D space occupied by B as omega. All right? So, we concern ourselves not with the body B itself, but really by the region in space that this body occupied, right? I've taken the body away. Remember the region in space that the body occupied? That is what we're going to concern ourselves with. Now, in order to be able to talk about this in a more sensible fashion, we need to introduce a little more mathematical notation here. And we will start doing that by introducing a set of axes, okay? For now, I've drawn three axes here because in general we're going to concern ourselves with three-dimensional space. And also for now I'm going to label these axes as x1, x2, x3. We will later on change that, okay? So the picture we have is the following. We have our body, right? It occupies some region in space. And in order to be able to talk about that region in space, we have this set of vectors, right? Vectors in 3D. Right? We can think about them as x1, x2, and x3, or x, y, z, or whatever you like. Okay? This is what reminds us that we're really talking about three-dimensional space. And that's what I've done by drawing the three axes here. Continuing with some more mathematical notation, we are also going to note that the region of space that we're truly interested in, omega, okay, which is now that region in space. This region in space, omega, is a subset of three-dimensional space, R3. Okay, R3 is how we denote three-dimensional space. The reason we call it R3 is that stands for real number and 3 stands for 3 dimensions. It just tells us that, well, we describe three-dimensional space through 3 numbers. You know what those 3 numbers are. They are the coordinates of a point, right, in three-dimensional space. The next piece that we need here is to remind ourselves that our body B consists of particles, right? So the body B consists of particles, say P, right? P is a particle. Now, what do we do about that particle P when we go to this representation of the body by the region occupied in space? Well, if that particle P lay there, if that is the particle P in the body, note that I'm using a sort of abusive notation because I'm using the particle P in the region of space occupied by the body, right? But we often use these interchangeably. Okay? Now, mathematically, again, it's no use talking about a particle. That's not mathematical notation, really. We need something else. Okay? Can you think of what that may be? Think about it for a few seconds and I'll give you the answer myself. Okay, if you've had a chance to think about it, we are going to use this idea of coordinates, right? In particular, we're going to use the idea of the position vector of that particle P. Okay? We're going to denote that position vector as x. Okay, we've already said that the body B consists of particles P. Okay? Represent, okay, what we're going to do is represent P by its position vector x, which really is just a collection of the coordinates of that particular position in space, right? So, some particle P sitting right here on the body, taking the body away, it occupies a position in space, and I'm still holding my finger here to remind us of that position in space. Here are our coordinates. We can now describe the coordinates of the position occupied by that particle P. Okay? And x is a vector. I'm using the same notation, x with an underbar. It's just a collection of the coordinates of the point, and that is how we represent it mathematically. Okay? We're going to stop here for this segment.